Okay, so in this video, we're going to keep talking here in this electric circuits world, and then what we're going to focus on is something called Ohm's law. All right. So one thing is that Ohm's law. All right, let me get this all set up. I should have probably done this before I started recording. So Ohm's law is an assertion that the current through a device is always directly proportional to the potential difference applied to that device. So Ohm's law is actually, it's a relationship, okay? So a conducting device obeys Ohm's law when the resistance of the device is independent of the magnitude and polarity of the applied potential difference or voltage, right? Now, the equation really to determine Ohm's law is R equals V over I, right? So we talk about how it's independent of magnitude, it's independent of polarity, right? So you can see there is a relationship. A lot of times if you search for Ohm's law, one of the search predictions will be something called Ohm's law triangle, all right? And so we got V, I, R. Okay, so another way to write Ohm's law is V equals IR, which is a very common way to write it, especially when you're doing things like Kirchhoff's laws, which is going to be here in a couple of videos. When you're doing RC circuits and RL circuits and LC circuits, right? So it's going to be a very important equation or version of the equation. You have the one that we just wrote, I equals V over I, R equals V over I, and then you also have I equals V over R, right? So it's just a relationship between current, resistance, and the potential difference. So the essence of the law is that the plot of I versus V is linear, thus making R independent of V, okay? And so really, a lot of times if you take just a basic physics class, they just say Ohm's law is the equation. But really what it is, it's just this idea that the plot of this graph is linear, and then which makes this idea that R is independent of V. So a conducting material obeys Ohm's law when the resistivity of the material, is independent of the magnitude and direction of applied electric field. Right, and so there we have another version of for an electric field. Okay, so it's going to be the electric field is equal to rho J, right? And so rho in this case is not density; it's that resistivity that we talked about in the last video. J is I over A, right? And so you can see the different versions of this equation that you can start writing out. All right, so here is an example problem. This is one we're going to look at the graphing and this idea that if this function is linear, then this material does obey Ohm's law, where the idea that resistance is independent of voltage. So a cylinder of material is attached to an ohm meter, which is a device used to measure the resistance of a material. The cross-sectional area of the cylinder cannot be changed, but it can be cut into different lengths. Given the following data about the experiment, produce a graph where the slope can be used to find the material's resistivity. Okay, so if you remember the equation, resistivity is the resistance is resistivity times length over area. So we have the R. Okay, so if I want this to be linear, I need to plot R versus L over A. So R versus L divided by A. If I plot this, this will produce a linear graph. If I did it just like versus length versus area, right? And then you've got other factors of the other one running around it. But if I want to produce a line, I would do R versus L over A, where the slope is now the resistivity, right? So what's the one thing that's still in that equation that is not boxed is that rho, which is the resistivity. So what I'm going to do is I'm going to fill in this box with L over A. And this is very typical of AP Physics free response question that's focused around analyzing data. They're always going to give you this extra column in the event that you have to plot something that is not what is provided for you there. Okay, so if I do L over A, for each one of these, I get 2.4, 1.9, 2.2, and 1.7. Okay, so what we need to do now is we need to kind of, and this is going to be a very rough sketch, so I'm going to sketch it, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is going to be my resistance. So this is not to 10, this is to 1. So I'm going to change this to a 1. So that means every tick mark is 0.1, right? Remember, resistance is in ohms. Make sure you're labeling your graphs. And then here we're going to go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So every tick mark is going to be 1, 2, 3, 0.2. All right. And this just helps me with my graph. And this is going to be my L over A, which is 1 over meters, or if you want to say meter squared, meters over meter squared. Okay. Or you can just say, in this case, it doesn't give us the units, but we know it's going to be, length over area, which is going to be 1 over length. And so I plot it. I go 2.4.72. Oh, let me go up to 3. So 2.4, 1, 2, 3, 4, 5, 6, 7. All right, about here. And I get 0.56 to 1.9. So 1, 2, 3, 4, 5, 6, just below that. Again, they're going to have a graph there for you. 2.2 to 6.52, so somewhere in here. And I go 1.7 to 0.5. So it's 6, 7. So it's going to be somewhere in there. All right, and now we're going to draw a best line fit. Again, this is a very rough sketch. And I know that the slope of this line will be my rho, my resistivity. So what I do, if they give you a nice data plot, you're going to find points that are on the best fit line. Remember, use your best fit line. Don't use, do not use the just simple data points to find the slope, because that's not going to be correct. I'm going to back this up a little bit. Okay, I'll make a line that goes through 0, 0. Okay, but another thing you can do is just use your calculator to do your stat plot, and I found that my resistivity is 0.3131 ohm meters, right? And because this relationship is linear, that this material that we have plotted does obey Ohm's law, okay? So in the next video, we're going to look at power. It's a topic that we've already spoken about, but we're going to relate it to electrical power at this point in time.